Okay, so today, my name is Jordan Parmer, for those of you who don't know me yet, and I'm a software engineer at Osberg. And a couple weeks, I think 2 months ago, I gave a talk on type systems, and we went over kind of like the very general introductory talk of what a type system is, and we talked about these things here, so went into type safety, static and dynamic type checking, and a few other things. Today we're going to do kind of a part two. But if you have not seen part one, that's okay. Because we're going to focus in particular on two new things today, which is going to be higher kinded types and type classes. And I'm going to try to do it through introductory code so you can kind of see how we build this up from scratch. Before I jump in, I just kind of want to give a brief review of what we talked about last time. If you're like me, whenever you got into functional programming, I came from imperative programming, a lot of object-oriented code, and so when I hit FP, there was a lot of new for me, and I had to unlearn a lot of habits, and I had to pick up some new habits. So if you're like me, one of the first rungs in the ladder you had to get up was just what does it mean to use immutable functions? Okay, that's kind of a good first step. So I have pure functions, they take an input, they give an output, and there's no side effects. So then you're like, okay, well, how do I write the code that I typically write adhering to those principles? And so there's a few tools that you kind of learn and patterns. You'll quickly get introduced to filters, mapping, reducing and folding, things like that. The next step up is when you start looking at these functions as little Lego pieces, as little building blocks, you start to look for ways that you can compose them together into interesting patterns. And that's where there's this fantastic intersect with maths. Okay, so we start getting into category theory and lambda calculus and type theory and a lot of the academic theories that sound really smart and impressive. And at first, that's kind of daunting, and I think that's why a lot of people are hesitant to get into functional programming, because there is such an overlap with these academic maths. But there is this intersection, though, that's like a sweet spot, where you can be a programmer in the traditional sense and realize that what we're doing is when we've reduced ourselves to some very raw principles of what a function is, we can reason about them logically using actual logic. And so any of the composition patterns that we get from these logical maths, we can bring into our code base. And how that's typically manifest is that we also have access to type systems and compilers that can reason about these things too. The more your type system and your compiler adheres to these principles, the better output you're going to get and the more sound your code becomes. And so you start getting into these higher levels of abstraction, and we're going to talk about that today a little bit with these higher kind of types and type classes. I also kind of want to note on the side, I think we see a lot of functional programming discussed these days in particular, because it's kind of going through a boom right now. I believe now that we're doing a lot of distributed computing and parallel processing, this serendipitously lines up with functional programming very nicely, because what we need to do is when we have multiple cores or multiple machines that we're computing on, we need to figure out how do we distribute computation across these, how do we process them in isolation, and then bring them back together into a single result set. And so a lot of our processing nowadays, we're concerned about these things, and again, that's a really nice overlap with FP that we have here. Okay, so we talked last time, what are the goals of a type system? And this is kind of what we bullet pointed out. We're checking for bad program behavior. We want to find problems as quickly as we can. And then we want to enable abstraction. So how do I hide the details that I don't care about and build upon abstractions and allow developers to make their own abstractions? And this was kind of the main point I wanted to highlight in the last talk. Really was the more you use your type system, okay, the more it works for you. So if you use your type system very primitively, you don't exercise it much, you can't expect a whole lot out of it. But when you really use your type system to enforce your domain, to enforce your algebra, we might even say, then you're going to be able to leverage a lot of these very powerful functionalities that come with it. So the first one we're going to explore is higher kind of types, and this is where we kind of left off last time. I didn't get to cover it, but it's going to lay the path forward for some pretty cool things when we talk about type classes. Now, higher kind of types are not available with a lot of the common, like, traditional programming languages. So whenever we talk about C++ or C# or Java, they don't get quite this far. And that's where having a more modern functional programming language can benefit from these. So let's talk about abstraction. Here's an interesting quote that I ran across. Type extraction is to leave out something that is not essential for the definition of a value or type, so that it can be varied, provided by the user of the abstraction as an argument. All right, so let's kind of see what that means here. So the very first thing we should look at is a value. And a value is just what we see here. We have 5, we have hello. We don't know much about those, but this is the lowest point of abstraction when we're thinking about programs. Now 5, what is that? Is that an integer? Is it a floating value? Is it something else? We don't know. It's just a value, all right? And so the next layer of abstraction is what we call a proper type. So that's when we actually put a constraint around what the value is or how it's being represented. So we're going to say here 5 is an integer, and that means something now. We're going to say down below, we're going to define a map data structure, and it's going to have those 2 values. So now we can map this across a domain of possible values. And then the next step, and if you're familiar with generics, it's very similar, although there are some nuanced differences here. But we have what's called first order types. And I'm sorry about the color there, it's kind of hard to read. The list, and then in brackets, we have something that's missing. If you're coming from a C-based language, you got the angle brackets instead of the square, but you get the idea. In other words, there is a type here that is to be determined or can be more like a wild character. Sometimes you'll hear it called a slot. Sometimes you'll hear it referred to as a star or a hole. But essentially, we're waiting for an argument to tell us what the type is. That is also, technically, that is a function. It is a function that is going to generate a proper type when we pass in an argument. It's also called a type constructor. Now this is where we start to become more unique compared to other languages when we get into the second order types. And there's a certain syntax here. Now there's the trait functor, that's not important, but what's important is what's on the inside. We have an F with a slot. And so what this means is we're technically abstracting over an abstraction. So we're saying that that inner type is going to be a type that is also going to abstract over a type. So it's second order. We're making 2 hops there. Now, that may not be really clear why this is helpful, but let me show you an example. Okay, so just kind of showing you this is the lowest to highest abstraction. So values all the way up to second order types. Okay. Okay, so I'm in my Scala REPL here, and I'm just going to type in some code. And this is going to be Scala, but it should be something that's pretty easy to understand what we're doing, even if you're not familiar with Scala. So the first thing we're going to do is we're going to create a trait or an interface, if you will, that is going to expect a second order type. So trait, we're going to call it a functor. Okay, does anybody remember what the purpose of a functor is? A functor, coming from category theory, is the principle that we want to transform something that's in one category to another. More simply put, we want to take something that's going from A and B. So we're just providing what's called a mapping function from how do we go from A to B. Since we are writing programming, we are in the category of types. So typically you go from one type to another. So maybe I want to go from an integer to a string, or a string to some custom type. And so that's what we're going to model here. We're just going to have one function that says I take an input and I convert it to a different output. So that function is typically called map. And what we need to do is we need to just take two types, the type that we have to begin with and type that we want to transform into. And so in order to do this, we're going to take a function that goes from A to B. And I could stop there and just say, okay, I'm just going to define a map function that does that. But what if I want to be able to go A to B when I have that value wrapped in something else? So whenever we're in functional programming, we'll often use things called monoids or monads where it's contained within something else. Or maybe you have a list of things. So I have a list of integers, and I want to convert that to a list of strings. Now, that outer list isn't really meaningful to my abstraction. I really want to transform the thing that's inside the list. If I'm in something like Java or C#, I have to be very explicit about that. I have to know what I'm traversing through in order to get to the values on the inside. When I can leverage higher kind of types, I'm able to abstract over that outer wrapper and then get to the stuff in the middle. So let me show what that looks like. Okay, so with this definition, we can see that we're going to take a map function. It's going to take a type A and a type B. The next parameter is going to be a function. Okay, we're going to pass in a function to this that converts it A to B. And then what we're left with is a function that when we pass in some type, f of A, we can return an f of B. So let me implement that. Let's say we're working with option types. Okay, so what I've done here is I said, okay, let's implement this for option. So I have an option of type A. I'm going to return an option of type B, and then I provide the implementation of that, which isn't really as important here. So what I can do is I can call this my functor. Oops. Thank you. Okay, so what I've done is I've applied the type that I want to abstract over. I've created an option that holds a value that it's an integer. And so now I can say my functor, I can pass that in. And then you've noticed at the bottom what it's returned is an option of type string. So what I've said is that I can create all these abstractions. Where I'm saying, okay, let's say you've got a bunch of boxes, and inside those boxes is a value. Those boxes might be different shapes, okay? They might represent different things. I can abstract out the fact that there's a box or some sort of container, and then I can provide implementations that get applied to the inner value of inside that box, which is what I've done here. So whenever I'm actually calling this, it'll go inside the option, transform the values, and then return me another option on the output. So there's a certain notation that comes from type theory called star notation. So if we have a value, let's say string, we say it's of kind star. That's an order 0, and it's a proper type. If we have something that's like a list that has one type slot, that's how we denote it. It's a star, arrow, star. Okay, that's an order 1, and what it does is that it's going to take an order 0 type, and it's going to produce a proper type from that. And this is actually the same thing. We have 2 type slots, but we're still going to produce a proper type at the end. So we're going to take 2 order 0 types, and we're going to produce a proper type. So if I were to put in map of an integer and a string, I have a proper type at that point. There's no more arguments to be taken. Now this guy here, the way you denote that is you put the stars in parentheses. So what we're saying is that we're going to define the first proper type, and then we're going to pass that in to generate the second one. So we're going to take an order 1 type, and from there we can produce a proper type. And so that's order 2. So anyway, you don't run across these a whole lot whenever you're writing your own code a lot of times, but whenever you're using what we're going to talk about next, we get into type classes. Type classes allow us to achieve some really cool abstractions in our code base. And a lot of how those work are by using higher kinded types, where essentially we're allowing for multiple layers of abstraction to get to the actual value on the inside. So if this didn't make sense, hopefully it'll make sense by the time we get done talking about type classes. These are some of the most common languages that support higher kind of types. Haskell and Scala, PureScript, OCaml and certain ML variants support it. Any questions so far? Okay, so let's talk about type classes. To me, these are absolutely fascinating because you can do some really neat things with type classes. They're also known as Adhoc Polymorphism. So when we talk about polymorphism, there's really 3 main things that you think about. There's what's called Subtype Polymorphism, which if you went to university to learn your coding is probably the first one that you approached. The whole idea of object inheritance is an example of subtype polymorphism. There's Parametric Polymorphism. That's what I was demonstrating earlier, where you've got a list of something. A lot of times we call that generics. That is Parametric Polymorphism, where we have type constructors, and we're waiting for arguments to define what the types are. And then we've got this third one, which is Ad-hoc Polymorphism. And this one's maybe not quite as familiar to circles outside of functional programming. So subtype polymorphism looks like this, okay? And this is probably familiar to most of you. So let's say that we have our base type is fruit, and then we have a whole bunch of subtypes. So we've got apple, banana, pear, watermelon. And the base fruit type can provide a function, and maybe it's defined with a default implementation or not. And then it's up to the subtypes that can override what that function is going to be. And it won't be until runtime that the proper function is called. So depending on how the polymorphism works, I might be calling it on an instance of an apple or the instance of a pear. It just kind of depends at runtime what happens. And then this is parametric polymorphism, where we're defining a type, and we have a type constructor. So we're going to say that this is going to wait for an argument type to tell me what this actually is. And this can be checked at compile time. So let's talk about ad hoc polymorphism and what that means. Okay, so here's a quote from John DeGoes. He is very active in the pure functional programming community. He's one of the maintainers for Scala Z, and you see him a lot in Haskell circles as well. He says, type classes, object-oriented interfaces, and ML-style modules were all invented to solve the same exact core problem. How do we abstract over a set of functions and types that might have multiple concrete implementations? Okay, so let's talk about inheritance for a minute. We did this last time, but let's just kind of remind ourselves, what are the disadvantages of inheritance? Aaron. Yeah, so yeah, he was saying that you might implement something now, but then later on down the road, as your domain changes, you've got, you have to potentially modify your entire inheritance structure to work with that. Or worst case, you leave it as it is and you bolt on abstractions that don't make sense. That can be a real problem. I think probably all of us at some point have been bitten by that, where you get this really elaborate inheritance chain, and then you try to change something in there, and you have to make a decision on, do you refactor the whole thing, and does this thing touch this thing, does it touch this thing, and it's not as decoupled as you thought. Any other problems? Yep. You confuse subtyping with code reuse. Absolutely. Sometimes we're just really bad at getting that abstraction right. Sometimes you might say, I need something that looks like this. I can use inheritance and I can inherit from that to borrow those properties. But really that, remember, inheritance is supposed to be an is-a relationship. And sometimes it's like, no, that really isn't one of those. You're just borrowing from a lot of the code and structure that's already there. And so by violating that encapsulation, you've now, coupled a lot of your code together in ways that don't make sense, which will just snowball into a bigger mess. Yeah, any others? I know for me personally, I hate finding stuff. Oh, go ahead. Mm-hmm. Yes, absolutely. And I was going to say too, I think just finding things can be difficult, especially when you have like 10 layers deep in your inheritance chain, and then you're like, well, where's this function coming from? Oh, okay, I'll go up this layer. Oh, okay, I got to go here. Oh, I got to go here. And it turns out those, sometimes they'll have like implemented, generic versions in there, and then you just got a whole mess trying to find stuff. Some IDEs are really good at helping you with that, but if you're just using like a text editor, you're kind of hosed. Dylan? It's a static relationship. Yeah, once you compile it, it's there. Okay. A lot of times it's easy to violate encapsulation because at different layers you can you have access to something else's members, and so you can either override those or change them, and so it gets really hard to control the state of the thing on the inside. I think we covered most of these. All right, so then we have interfaces that kind of come next. How do those improve things? A lot, yeah. What's the difference between the interfaces and the inheritance? Yeah, so we're defining, this is an expected behavior, but it's not the actual like object itself. So we can say this object is now going to provide an implementation for this behavior, but all of our functions can just say, well, I expect something with this behavior itself, regardless of the implementation. Mm-hmm. Yeah, so we find ourselves being able to get one step closer to separating out the actual implementation from the interface itself, which is nice. Now, where do interfaces fall short, though? Because it's not all roses with interfaces either. Yeah, so interfaces, one of the things that's tricky about them is that you have to actually own the code base to apply the interface, all right? So when you're writing your own objects, you can say, this is the implementation of it, and here's how it conforms to the interface. If you don't own it, like let's say you brought in a library, it gets trickier to work with that. You have to like write a wrapper object around it and try to kind of shim the behavior that way, which isn't always elegant, especially if you brought in a large library. Now you've got like this massive set of wrapper classes that you've got to bring in. Also, has anybody seen interface versioning get out of hand? Where it's like, I have this interface, and then I need to add a method to it, but I'm not supposed to break that contract, so I have like a version 2, and a version 3, and a version 4. I've seen some companies that I'm not going to name that are very big that have really large interface-based APIs, and they literally, as a convention, will put a number at the end of it, and some of their numbers get down to like 9, 10, 11. It's like, how many interfaces do I have, and which one do I bring in? So it's difficult. All right. So with type classes, one of our goals is we want to separate data from behavior, but we want to make that a little bit more flexible than what we get with just interfaces. So I'm going to kind of just code up some examples here. I'm going to first do this in Haskell to show you how easy it is in Haskell, because this is a first class concern in Haskell. And then I'll show you in Scala if time allows, which is not quite as easy, but it's also there. Wrong one. Okay, I'm going to use an online REPL for the Haskell stuff. And I don't know Haskell very well, so be lenient on me here. Okay. So in Haskell, pretty much everything in Haskell is done through type classes. You don't have in Haskell a data structure that also has functions built in with it. Everything's separated. So you define your data structure, and then separately you define how it conforms to various type classes. And then you ad hoc bring those type classes in the scope, and that defines what you can do with the data structure. So it's not too far from what we're used to, but it's a complete separation. And really all of the basic stuff that you can do in Haskell is probably reaching out to a type class somewhere behind the scenes. So even when you're doing like things like equality or printing to the screen, that's leveraging a type class for that particular type. All right, so remember there's a very common pattern that we talk about are monoids. And a monoid is just the ability to append two different things together. It also has an identity state too. Otherwise, it's a semigroup. But I just want to be able to append two things together. So integer addition is a monoid pattern. String concatenation is a monoid pattern. All right. So we're going to define our own monoid, even though there's one built in. We're going to define our own. So we say my monoid A where, and then we have to define the empty case. Oops. Why are you doing that? Okay. And then we defined what the append looks like. So here we're going to, this is where we're just defining what the type class, the behavior is. The behavior is you have two functions. An identity, so that returns some type A. Okay, so if I have an integer, the identity for an integer is 0. So I'm still returning an integer type. I'm not returning something else. And then appending, I'm going to take two of the same type and produce a result that's of the same type. So when I add two integers together, I also get an integer. Okay, that's the monoid law. All right, so let's define this for integers for starts. So in Haskell, we say instance of my monoid for type integer, where, and then we say empty is going to equal 0, and we're going to say append A and B equals A plus B. Now I could have done multiplication or some other crazy thing in here, but we're just going to do A plus B. So when we run this, we can now say append 1 and 2, and we get 3. All right, and that's using what we've defined here. So I don't have access to the integer source code here. Okay, I'm not extending that to fit an interface. It's completely separated to find somewhere else. But outside of that, I'm able to say, here's a behavior, and here's how that behavior is implemented. And then I can bring this into scope wherever in my code base I want to, and I could expose it as a library that somebody else could bring in. I could have easily changed this to multiplication. Run that again. Let's do something more interesting. And then we get 6. All right. Okay, so let's do this. I'm going to skip to a custom data type. Let's say we're going to create a custom data type called foo, and it's going to have 2 integer values. And ignore that for now. So we're going to set both of those integers to 0. I think I did that right. Nope. Oh, thank you. I totally transposed my lines there. Transfer, deriving, show. Yes, thank you. Okay. Instance, my monoid, foo, where? Okay, that should work. Okay, so over here, I should be able to say foo, 1 and 2. Okay, that defines like a foo. So I could say append foo 1 and 2 with another foo, like 2 and 5. And then I get foo 3, 7. Okay, so right there, I've defined a custom type and then provided a type class, which is just a behavior, and here's what that behavior looks like. And you can have multiple versions of these things too. So, built into the standard library, there is a monoid type class. But what I've done here is I've shadowed over that and said, well, here's what that behavior is. Now that can get you in trouble because if you have a whole bunch of type classes that expect the same type signature, which one does it resolve can be a bit fun to figure out. So, we've improved things a bit, and we've also created some other swords you got to be careful with. Okay, so let's look at this in Scala now. Hopefully, I can cram this into the time I have left. Okay, so in Scala, we can do type classes, but it's not a first class concern of the language, unfortunately. So what we have to do is actually conform to a pattern using some Scala language features. They can be used for other things, but type classes are a really good fit for them. So when we're in Scala, let's take the example. We want to, the same thing, we want to append two things together. So what we would like to do is create a function that roughly looks like this. We want to take append items of type T. We're going to have a left T and a right of type T. And then we would like to return a T. And so what would be really nice is if we could say left append right. Okay, that's what we would want this to look like. And then we'd want to be able to say for any type that we have defined this behavior for, it will choose the proper thing at compilation time. Okay, so let's define that. And what we do in Scala is we define a trait with the behavior that we want. So if you're familiar with interfaces, traits in Scala are very similar to interfaces. There are some differences, but you can generally think of them that way. Okay, so let's say trait appendable T. Here's the function that we want. And then now that we have our traits, we need to provide implementations for the various data types that we care about. So let's create this for integers, and let's create it for strings. Oops. And this is, if you're familiar with Scala, this is relies on implicits, which I'm not going to get super deep into here. And then let's define it for strings as well. Okay, and so what we'll do is down here we'll say we'll have to import the implementation into scope. And then we can now provide the implementation. So we can say val result1 equals append items 2 and 3. We can say result2 append items A and B. And I'm probably messed that up. No, that was oh, I did forget something major. I need to provide my actual call here. So def append items. Okay, so as you can see from the results, we get, it's appended the 2 integers to generate 5, and it's appended concatenated the 2 strings to give me A and B. So let's look at this code again. So up at the top, we've defined, here's what our behavior that we want. Here are some example implementations, one for integers, one for strings. And then what we can do is we can define a function that says, okay, you can call this function for these inputs of type T as long as there is a type class of type T within scope. And then as long as that's there, the code will compile. This is all done at compile time, which is also a benefit over the subtype polymorphism, which is done at runtime. So we know at compile time if that behavior is in scope. And if I were to take that behavior out of scope, then I'm going to get a compile error saying, hey, you're calling this with integers or strings, and I don't know what those are. Yeah, could not find an implicit behavior for that parameter of integer or string. So here's where this is really handy is in Scala, there's 2 major libraries that have a lot of type class helpers in them. You'll hear of Scala Z or the CATS library. And what they do is they bring in type classes for a lot of the functional programming, kind of category theory behaviors. And so when you bring those into scope, suddenly all of your data types can cooperate with these behaviors and operators without you having to actually own the code base for those operators yourself, which is really handy. I'm out of time. I had a much more elaborate example. We're going to use this with a custom data type, but I'm just going to put that in the slide notes on Meetup later. But that's kind of the general idea with type classes there. Does anybody have any questions about that? Scott? Okay, so the question was about the scoping. Appendable ops, I have defined this in this particular namespace, this particular like Java package. And so I can import that into whatever scope I need it to. So you're right, I could technically, well, the way Scala works is that in order to bring in, okay, sorry. If I did not import that, I would have to fully qualify the reference here. I think that's what you're getting at. So the fact that I have an object appendable ops, if I wanted to reference that here without the import, I would have to say appendable ops dot appendable. Or I could use this import command, and that brings it into all the contents of the appendable ops is brought into scope. And there's some clever ways, like the people that typically produce type class libraries, there's some clever ways of bringing most of that into the global scope wherever you want it at. All right, any other questions? Okay, cool. Well, thank you for coming today.